Okay. All right. Yeah. Thank you, everyone, for first. Thank you for the invitation. I'm really excited to be here, and thank you all for sticking around. I know it's the last talk, so I'm glad there's a sufficient audience here.
Put you guys first.
Maybe next time. Okay. So yeah. So I'm Gokul Ravi. So I just started here a month and a half ago as an assistant professor in CSE. And I guess, just started my research lab, which is called Kafka, stands for Computer Architecture for Quantum Advantage. So, and my research is essentially at the intersection of quantum and classical computing. So I actually did my PhD in classical computing, traditional computer architecture, trying to build faster and more power efficient CPUs. And from there, for my postdoc, I got interested in quantum, and so I went to Chicago and I worked on that. And then I sort of got interested in research, which sort of brings these together, which is especially important in the now, because the last 20, 30 years, initially there was, of course, a lot of research in the theoretical sides of quantum. And then maybe at the beginning of the 2000s, there was like the beginnings of the experimental research in terms of building qubits. But now we are at the phase where we do have quantum computers. They're still small size, they have a lot of flaws, but we are on the trajectory to actually build systems which can be impactful, right? And this requires more than just theory and experimentalists and people who work in the systems domain as well. Okay, so so in this talk, I'm going to sort of structure it as a little bit of introduction and background on quantum, so a little bit overview of my research, and then I'm going to talk about one of my specific projects. And the reason is that, considering this is a pretty broad audience, I can't assume that the nitty-gritties of quantum, which so I think the big learning aspect would be the quantum itself, as opposed to the specific project which I'm going to introduce, right? So, okay, so what is quantum good for? It has the potential to be useful for a wide variety of research and scientific and medical applications. So, for example, drug discovery is definitely one of the key areas which is driving this, driving quantum. There's also opportunity in industrial chemistry through material science research, optimization tasks in transport and supply chain, some intersections with machine learning, and also applications to finance, security, and more. Of course, all of this is in the long term, though some of them are easier to achieve than others. And all of this has resulted in significant interest from both industry in terms of the larger big tech giants, as well as smaller upcoming promising startups, as well as significant investment from national governments across the world. So what is it that enables quantum to have its benefits? So which is potentially a semester or a year's worth of lectures, but I'm just going to condense this into, I guess, 1 or 2 slides, right? So the high level idea is that a classical bit is, for example, implemented with a transistor, can take the values of 0 or 1. On the other hand, a qubit can simultaneously be in the 0 state and the 1 state at the same time. Okay, so it can essentially be anywhere on the surface of the sphere, which is known as a Bloch sphere. And depending on where this arrow is pointing, that is where it is on the sphere, there is a different weight to whether it is closer to the 0 state or the 1 state. But the key thing is it is in both states at the same time. Okay, so from a computational perspective, what this means is that a single qubit can sort of simultaneously compute over 2 classical 1-bit states, which are the top and bottom over here. And n qubits can kind of simultaneously compute over 2 to the power n classical n-bit states. Now, I say kind of and have this constraint thing over here because this is not the equivalent of, say, having a GPU which has 2 to the power n parallel multiple threads, right? There's a little bit more to it, which I can't get into now, but I'm happy to talk about offline. But the key idea here is that because of this capability, there are some applications where there is a significant, potentially exponential computational benefit over classical computers, which is what is known as quantum advantage. Okay, so how do we manipulate these qubits? We manipulate them by building quantum circuits. And at high level of abstraction, these circuits look similar to the kind of digital circuits you're familiar with. So in this case, we have a 2-qubit circuit on which we are applying what these are called like single qubit gates, which essentially means you're hitting these qubits with some particular pulses at some particular frequency, which is basically manipulating the state of these qubit along that sphere, which I showed earlier. And you can have these multi-qubit gates, which can sort of be broken down into 2-qubit gates, which allows these different qubits to interact with each other, which is what creates that 2 to the power n interaction, right? So once you execute your quantum algorithm, which is implemented as a circuit, you do a final measurement because you need to observe what the quantum computer has done. And this observation sort of brings us back to the classical space, and therefore you get some particular bit string. And if your circuit is implemented correctly and your device is pretty good, this classical bit string is the answer to some very hard problem, right? And again, the key thing, which is a follow-up to my previous slide, what I said is that internally, this is computing over this 2 to the power n states, but the final state it produces is just a bit string. All right, so in order to build these quantum circuits and qubits, there are multiple very promising technologies which have made a significant advancements. So I've listed 3 of them here: superconducting neutral atoms and trapped ions. There's also a lot of research at Michigan in terms of in the space of photonics and so on, which is also promising, but perhaps a more long-term domain. So while each of this has a lot of potential and has been making significant advancements, there are limitations to each of this, which again, I'm happy to talk about offline. The one thing I want to mention is that today these limitations are pretty significant, which is why we are in this regime we call NISQ, or noisy intermediate scale quantum, which basically means we have few qubits and these qubits are of fairly poor quality. Now, these devices will keep improving, but to some extent, these limitations are going to be fundamental. So we are never truly going to achieve a fidelity of a qubit similar to the fidelity of a transistor, which means we have to build mechanisms around these qubits so that they're able to deal and work in the presence of these errors. Okay, and there's a bunch of techniques which we can use to do that. And these different errors, and which I mentioned earlier, they can affect the circuit at any point. So for example, it can affect it right when you initialize these circuits. When you apply these gates, these 2 qubit gates, they also lose their state over time, which is called decoherence. And also, they also, like when you measure, also you can have errors, and all of these errors essentially means that the direction the vector is pointing on the sphere is changing, and which means you're going to a wrong state. Okay, so these are the things you have to deal with. Okay, so what I've told you so far is that there are a bunch of promising applications, there are new applications are being founded, and there's active research in this area as well. And device capability is continuing to increase, especially it has accelerated in the past 10 years. But there is still a very significant gap between what applications need and what devices are able to achieve. And closing this gap is perhaps the most important billion, maybe trillion at some point, dollar question of the next many years, right? So, and how do we achieve this? Of course, we continue to need theoretical research from theorists and application folks who are trying to reduce the quality and quantity of qubits needed for these applications, as well as new applications which they continue to try to discover. And of course, there is research needed in terms of the experimental and the physics folks in terms of improving the capability of these devices. But that alone is insufficient to close this entire gap. But so what I'm pursuing, and what this has sort of become more prominent the past 10 years, is to see if we can use classical computing approaches, which broadly encompasses maybe existing techniques in the classical world, or just techniques which are inspired by things which have been honed over many years in classical computing, to help bridge this gap. Okay, and in order to do this, there are multiple avenues, right? So for example, which is very relevant to this community, is using the amazing tools we have been building for scientific compute. And then there are other aspects of research like programming languages and compilation, compute architecture, high performance computing, optimization, cryogenics, and much more, all of which can help in one way or the other to help bridge this gap. Okay, so it's a very open field which requires contribution from all of you, and many more folks whom you can get excited about this. And if you want to learn more, I'm plugging my course. So I'm going to be teaching a hybrid quantum systems course in the winter. So if you or your friends want to attend this course, please, please, I encourage you to do so. Okay, so that's sort of the background. So now a little bit more about my own research. As I said, I work on sort of a hybrid quantum classical ecosystem. Essentially, as a computer architect, as a systems person, I work at the sort of across the stack from applications to technology. Okay, so I broadly work in these 4 areas. One is classical application transformation, which roughly means what are the classical things I can do to an application before and after the quantum processing, so that it makes the quantum processing much easier. Okay, and this is what I'm going to talk about more today. Another area is adaptive noise mitigation. So noise mitigation is any technique which reduces the effect of noise on qubits. Now, physicists have come up with amazing methods to reduce noise in qubits, but usually these are focused on a single qubit or maybe the interaction between a pair of qubits. And these techniques have limited capability to scale to, hundreds of qubits today or thousands or millions of qubits in the future. So I've been building techniques which are either domain specific or general, which can sort of dynamically adapt to the needs of applications and quantum devices. Another area is error correction or scalable error correction. So quantum error correction is another very important future domain where we use, similar to classical error correction techniques, which many of you might be familiar with, there's a need for error correction in quantum as well. And while in theory, this is amazing and it can solve all your quantum problems, it's very hard to actually implement and build. So I've been working on building scalable error correction techniques. And then there's efficient resource management, which is sort of a broad theme. But some of the themes involved in this are just resource management in the cloud, for example, right? So because there is a need, we have some quantum resources, there's a lot of demand. We need to build schemes which we can, better make use of the best device or the best application and so on. In fact, these are kind of areas where this is a sort of a path of least resistance for students who get involved in quantum, because it involves some quantum, but a lot of the research is in classical computing itself. Okay, so a lot of opportunity in this space. Okay, so let's get to classical application transformation. So as I mentioned, the idea is that any given application which has some potential for quantum benefits can be viewed as this pie chart. So there is a significant portion of the application usually which is classically tractable, which means that it can be efficiently run on a classical computer. And there is some portion which is, of course, interactable, which is why you think this is an application suitable for quantum computers, right? But if you force this to run on a classical device or a classical computer, it is this blue component over here, which is going to take up most of your runtime, because there is an exponential cost to running this. So how do you actually run this on a quantum device? You want, of course, send this blue portion to your quantum device, but you want to do this yellow portion on a classical computer. And this is, in fact, it's better to do this for every reason possible. And this is because if you run this on a quantum device, the quantum device is going to be noisy, or you need a lot more resources to compensate for this noise. Quantum resources are always going to be very expensive, so there's a lot of cost involved. And quantum resources are pretty slow as well. They are much slower than a classical computer, right? So it's only useful to use a quantum device for the portion of your application which truly needs a quantum computer, right? And this gap between this blue and this yellow is not necessarily well defined, right? If you talk to a theorist, they would say that, oh, this is the exponential portion of the application, this is the polynomial time portion of the application. But this is not how real computing works, right? It's more like, I have this particular classical computing resource, I have a 1 megawatt budget or 1 day on this. How much can I do on this in this budget before I have to go to the quantum device? So, and what I'm saying is that this separation over here is really dependent on what you are able to achieve, you and the entire community is able to achieve for these applications. And it's very important to think about this, especially for the scientific computing community. Okay, with that, I'm going to talk about one specific proposal. Let's see, how am I doing on time? Do I have like 5-10 minutes? Then, okay, that's good. Okay, so I'm going to talk about this work called Kafka. Note that my group is also called Kafka, and this project is also called Kafka. You can understand my philosophy in life, but it's not the same Kafka. Okay, so exactly. So Kafka here stands for Clifford Ansatz for quantum accuracy. And the idea here is based on the classical transformation I showed earlier, that you're trying to use classical compute to get a very good initialization for a particular quantum problem. And that's what I'm going to explain. And sort of the key highlight of this work is that it is able to recover more than 99% of the accuracy which has been lost in prior initialization methods. Though I want to revisit this point towards the end. Okay, so the focus of this is this topic called variational quantum algorithms. So what are variational quantum algorithms? So the best way to think about this is first think of classical optimization, right? Which you are used to thinking about in just for optimization problems, machine learning, and much more, right? The idea is that you have some optimization contour, there's some objective function, you're trying to find this global minimum, right? And so what you do is you start somewhere and you do something like gradient descent, and hopefully you're able to find this. And each of this points over here, you're evaluating on a classical computer, right? This is essentially how your optimization process works. So variational quantum algorithm is very similar to this, except that each of these evaluations has a exponential cost involved. So maybe, for example, you're trying to understand something about, say, electron-electron interactions, right? Which makes this a hard problem, which is why each of this objective evaluation needs to happen on a quantum device. If this was perfect and this was ideal, then this navigating this contour is no harder than navigating the contour from the classical problem I showed earlier. But unfortunately, quantum computers are noisy. They are very noisy today. They are going to be less noisy tomorrow, but they are still going to be noisy. And what this does is that even for optimization contours, which are fairly smooth and which have like some nice gradients you can follow, noise makes this much harder, right? It fills it with a bunch of spikes because noise affects the objective evaluation in many ways. So it basically creates like positive, negative errors and so on, which means that you have things like these noise-induced minimum. You also have some regions, which is not very well shown here, but some regions where your gradient might entirely disappear. So it's hard to make any forward progress. And so it's hard. So it's hard to find this golden star. Okay, so, and therefore what I'm trying to motivate is that finding good initialization is really important. Okay, so in this work, Kafka, what we do is that there's a key insight that even though this contour itself is essentially a quantum contour, there are some specific points, these discrete green dots over here, which correspond to something known as Clifford points, which can actually be run efficiently in polynomial time on a classical computer. Okay, so, and because you're running on a classical computer, it's noise free, right? So you get essentially all of these green dots for free. And if you're able to do this, you are instead able to do like run instead of running like a continuous optimization algorithm, which is what you would have done normally, you would run a discrete optimization on this so that you can find the best or a few of the best green dots, so that you can then restrict your variational algorithm to either start from your best green dot or restrict it to the space where the most prominent green dots are present. Okay, so now, of course, you can ask the question, what if this green dot just happens to be good, but in fact, it's not necessarily near this global minimum, right? Of course, that is possible, right? And but usually in problems where your contour itself is reasonably convex, and which is often the case in a lot of these problems, but it's just that the noise is making it much worse. This initialization often gets you really close, and empirically we observe that oftentimes we get more than 99% accuracy, right? So, and of course, there is other, maybe you can use some information you know about the domain to throw away some of these green dots because you think they will not be useful. But the point is that it's able to help you eliminate a huge portion of your noisy quantum search space, so that you have to throw your quantum resources at a much smaller portion of the problem. Question.
How do you find the Clifford point?
I'm going to get into that.
Okay.
Yeah, so it's exactly, that's the main question to address. Okay, so, and yeah, so in the next few minutes, I'm going to discuss how we find those points and what we do with them. Okay, so a little more detail on how these variational algorithms work. So I've already told you that basically there's this contour and you're trying to find this star. Okay, and this has applications in chemistry, optimization, and much more. So the idea is that you're going to try to generate a quantum state, an arbitrary quantum state. The quantum state is passed through some mathematical function. That mathematical function is derived from something you know about the problem. Okay, so, and once you pass it through the function, that gives you this scalar, which is the objective function value. Okay, so how do you navigate the space? Is basically you want to produce different quantum states, right? You want to, hopefully you keep producing quantum states, which takes you towards this one. And in order to produce these quantum states, we use something known as an ansatz. An ansatz is just a parameterized circuit like the one shown over here. The structure of the circuit, which you can think of the skeleton with the 2-qubit gate over here, is maybe something you can derive from something you know about the problem itself. But all of these single qubit gates are tunable, right? So all of these gates can go from 0 to 2 pi, which, as I said earlier, means they're going to different positions on the sphere. And you have a classical optimizer. This is just a classical optimizer, which you might use anywhere else to tune the values of each of these gates. And how does this work? It's because it's doing something like a finite difference method based on the objective function values it's calculating here to set these values. And this is what you're going to tune so that you go down this contour. Okay, so it's great. So now this comes to where this Clifford aspect comes. Okay, so this was the parameterized circuit I showed you earlier. All of these single qubit gates can be tuned. And this is an example of a general quantum circuit created with this thing. So you can see all the angles like pi by 3, pi by 4, and so on. This is a typical interactable circuit, needs a quantum device, maybe not for 2 qubits when we go to like 50 plus qubits, right? That's where a classical computer cannot do anything anymore. On the other hand, if you, in this kind of construction, so this is kind of an example, but in this kind of a circuit construction, if all of these single qubit gates are only multiples of pi by 2, this makes them these makes all of these gates Clifford. And if all of these gates are Clifford, the circuit is overall Clifford. And then we know from this Gottesman-Cannell theorem that this can be simulated in polynomial time. So basically, we have reduced this problem to a discrete search on gates which are just multiples of pi by 2, and therefore that is only going to search through those Clifford circuits, right? And this is basically what Kafka does. So it's just searching through this, the same parameters, but more restricted values. In the initial work, we used a Bayesian optimization algorithm to do this discrete search, which I'm not really going to get into. So you can imagine that. So it uses like a random forest-based surrogate model, which is nice for discrete optimizations. But the key takeaway here is that it's good at finding those points. Okay, so what do we achieve with this?
How do you know that the Clifford points like span your domain? How do you know that you're on either side of the optimum?
Well, okay, so it doesn't have to be either side of the optima in some sense. You're just trying to find a few set of good.
The Clifford points are on one side, right? And everything on the other side has to be simulated with quantum, right? Then your BO always has to then be running quantum, right?
Well, I mean, okay, so technically, it depends on what you mean by either side, because these are discrete points in the space, right? So your correct quantum space
function, right?
Yeah.
That objective function you can evaluate cheaply with some set of some set of points that are, I guess, have some symmetry that allows you to do that classically, right?
Yeah, I think the way to think of it is that let's say that your space was this a square. Okay, so the Clifford points might be the corners on this on this thing. So I'm trying to find the corner which gives me my best estimate, and my assumption here is that the correct answer is going to be close to this corner, which is usually true. I mean, because spaces are usually have there is some amount of convexity to spaces. So that's all my Clifford point is doing. It's trying to find the corner of this thing. Okay, so if that makes sense. So in some sense,
we can pick it up later.
Okay, sounds good. Okay, the point is, in a lot of problems, we don't have any informed initialization, and this is a pretty useful initialization. Okay, so I'm just quickly going to show one result for this, which is in terms of a typical initialization which is used for these problems is the Hartree-Fock initialization, because the Hartree-Fock is essentially creating a good bit string. And so Hartree-Fock initialization is the starting point over here. After this, which you run your variation algorithm, and it takes a long time to converge. For this particular problem, which is lithium hydride, the Kafka initialization is near perfect just to begin with. Okay, so it's not perfect because there is some quantumness to this problem, but you can see that in just a few, in like 80 iterations or so, it is able to converge, which is which is great, and that's for this 100x higher accuracy to begin with, and also very fast convergence. And we observe this for a bunch of problems. I'm happy to talk about more in the chemistry space, and also work from the physics space and a bunch of other domains as well. So am I out of time? Okay, so I'll just leave you with a couple of points. There's a lot of potential for pursuing optimization in terms of improving the quality of these algorithms. For example, with genetic algorithms, we found that we are able to get like 3 orders of magnitude improvement, which means that even for like 100 plus qubit system, we're able to like get these very good Kafka points in like less than an hour. And okay, so I'll just stop with this one. So the point I want to make here is that Kafka itself it looks at only Cliffords, and Cliffords are polynomial time, right? On the other hand, it is possible to go a bit beyond polynomial time in terms of by introducing some amount of non-Cliffordness into your circuits. Okay, so in this example, these T gates are basically non-Clifford elements. And you can see that just, again, this is a small molecule. So this is the green line is a Kafka initialization. the purple line is this Kafka plus one non-Clifford initialization. You can see how close it gets you to this orange line, which is the exact line. So the point I'm trying to make here is that given that you have some classical compute capability, which is maybe a laptop, maybe a desktop, maybe a supercomputer, there is some amount of non-Cliffordness that supercomputer can handle, right? So, and again, from my example earlier, say you have 1 day on the supercomputer, right? So your real goal should be, how far can I go close to this, to my best possible solution before I tap out and have to go to the quantum device, right? And this could be with a completely domain agnostic method like Kafka, or it could use a bunch of other classical simulators, state-of-the-art scientific computation tools, some machine learning techniques, some domain-specific theory, and so on. I also think even doing Kafka and these quantum things on small molecules can be plugged into machine learning stuff. I had this slide from earlier, but I think it also relates to what Venkat presented, that even doing this for reasonably sized but hard molecules can help impact very significant domains of interest. And I'll stop with there. I want to just give a shout out to Jose, my undergraduate student, who is looking at things like quantum plus computational fluid dynamics. And I think he would love to talk to more folks over here. And I'm excited to work with MIT to pursue these domains. Yeah, thank you. Questions? Yeah, good.
I don't know much about the points, but do you still get entangled states with tools, or are those like completely for the state?
Excellent question. Yes, you do get entangled states as well. In fact, that is one of the power of Clifford states going beyond like the Hartree-Fock state. Basically, it'll give you like a bit string. So it essentially gives you your electrons being in the upspin or the downspin. That's it. So the Cliffords, on the other hand, can give you an equal, it can create entanglement, and you can get like equal superposition or different states. And so it is basically a superset of what like Hartree-Fock can produce. And in fact, chemically, this is very useful, because if you go to like very large bond lengths for a molecule, all your forces are becoming sort of equally low, which means that your electron, for example, has equal probability of being in the upspin and the downspin at the same time, which is essentially an equal superposition of 2-bit strings, which is basically a stabilizer state, which is the thing that Clifford states can achieve. So, yeah, go ahead.
Can you like some ideas why is it that these points are so like?
Yeah.
Assume some regularity of the objective of the response.
For the Clifford points, so
it will be just
okay. So I think there are two separate questions. I guess your question is why should the Clifford point be a good point? Is that your question?
I think that's his question.
No, I think
his question is
why are Cliffords?
Maybe he should say his question.
We'll take an entangled state of all.
Entangled.
No, but yeah, it's like a two-part point. One is why
does Clifford points exist?
Are so easy to compute classically, and the other is, well, once you have those, do you need any regularity on the function that you're evaluating, so that those Clifford points like a good sample points to start your.
Okay, yeah, okay, great question. So the reason why Cliffords are classically simulable, so if you want like the total theoretic, you should read that Gottesman-Cannell theorem paper from '98, which but the very high level idea is that Cliffords basically are transforming Paulis into other Paulis. Okay, so in some sense, if that entire circuit, you don't have to simulate a circuit and have to search through the 2 to the power n space to go from the input to the output. Okay, there is a very structured method you can go through it. So which is why it's not like you're actually simulating the circuit. There are these stabilizer frameworks which are actually just doing the math which corresponds to those transformations, which is why it makes it very easy to do in polynomial time. Now, the second question is, does it have to be structure to the problem? Yes. So 2 ways I would view this is that one, as I said, I gave the chemistry example earlier, where for some problems, we know that these states are good states because, as I said, equal superpositions are actually useful states. You just don't know which equal superposition is the right state. Okay, so as I said, because you know that it's either this electron up and this electron down are both going to pair well with equal probability. You just don't know which pairs, right? So there are some problems where you can intuitively say that that there are some regions where the stabilized states are good. Now, there's of course going to be scenarios, though we haven't found any, at least in our chemistry and physics problems, where we might find this Clifford state and it is just such a bad like local minimum, and it's so tough to get out of because it's, yes, it is possible, right? So, and I would say that it's important, I guess, for any method which is agnostic to the problem itself. In this case, it is completely agnostic to the problem, that, yeah, you should be careful that you can get stuck in. And so it might be tough to converge, but again, empirically, yeah, we can talk about this more, but there are many reasons why we think this is a good starting point. Yeah, was there one more follow-up question?
Yeah, so I think because chemistry and physics, right, is fundamental. So it makes sense that those Clifford points are good ansatz for chemistry, and because you can imagine that the solution space is sort of, you know, some superposition of those Clifford.
Right.
states,
Yeah,
right?
and nature is smooth
Yeah,
to some extent. Yeah.
But I don't know if that necessarily has to hold for problems where that decomposition doesn't quite make sense, right?
Yeah, very possible. I mean, yeah, I would completely agree. And I think the one thing,
Like it totally makes sense that like for lithium hydride, like that problem, the way you formulated it makes perfect sense, right? Like it would make sense that the solution would be close to that, right? So
yeah, I mean, I think the point is, when it's very close, it's really nice. Like we get like it's 99 point something, but in many cases, like we know some particular problems where, for example, if you create like a very long hydrogen chain, we know that there is a lot of quantumness to this problem itself. So for example, we know we can create scenarios where the Clifford point is not great, okay, but it's still better than arbitrary initialization.
Because these problems don't have dispersion, right? Like they're local, right? Your hydrogen chain that has dispersion in that, like some small perturbation here is going to affect, you know, something far away, right?
Yeah, very possible. So I think it's important. So the reason why I pulled this up is because there are also other classical simulator techniques, like especially these some of these tensor network simulator techniques, which have other pros and cons. For example, going back to the earlier question, so Clifford